Welcome back. We are now into a very different kind of potential function model, which you will be using quite a bit, because most of the systems would use some kind of metallic system which are based on face center cubic structure in terms of their lattice model. So, this was the initial problem to get over the pair potential issues with the Cauchy's equality between C12 and C44, as well as we were looking at the relaxation of the metallic surfaces. So, that is when we thought about the system that will also include many body potential. So, the way you have to think about is that the atoms are in a background of a whole bunch of electrons, and so they have certain affinity towards where they are located. So, if you try to pull one out, what is the cohesive energy you have to get over in order to take that out, and that is where we can come up with the model of cohesion and then see, and that is where we call embedded atom. So, the atom is embedded inside the gallium of all these different other atoms or the cloud of atoms, and you have additional term which is now compensating for that embedded atom energy, which then gives you the right understanding of metallic behavior in terms of elastic constant as well as the relaxation of the surface. So, it was introduced in 1984 for the use in simulation of metals and alloys. These models are designed to take into account cohesive property of the conduction electron charge densities in an empirical fashion that is computationally tractable. So, the issue is also I can take care of all this cohesive energy, but how do I come up with algorithm or a potential energy I would say mathematical function that I can use in computers. Just like 612 potential in Lennard-Jones, you have very clearly defined mathematical function. And so, that is where the name comes from, the embedded atom method, where you have atom embedded inside the charge density of electrons. And this was done in 1984 by Michael Baskis and Dow and their associates. So, you can see a lot of references given here. So, let us start with understanding what does it mean to formulate an EAM potential. Number one, as you see on your slide, the EAM formulation one writes for the cohesive energy of the system. So, E is that cohesive energy, which if you look at all the atoms, you have I is equal to 1 to n, and but that is divided into two energies. One is sublimation energy at 0 temperature and pressure, which is E sub, and then you are also looking at another term which is coming out of the lattice parameter, which is embedded in this. So, that is where this F I rho I comes from, and then we also have a pair potential R I j, which is similar to the Lennard-Jones. So, if you go to the next slide, what you observe now, we look at the function that is embedding energy function F with the electron density quite remarkable, being a monotonically decreasing function as rho increases. So, we are looking at the density of states. So, it is based on the approximation of density functional approximation, which has been put right into it, and this rho is the density functions that is describing the density of states of electronic cloud that you are dealing with. So, in this case rho I is summation of from j rho j to R I j. So, if you look at two atoms here, there is multiplied by their what we call is the density functional, and it decreases with the distance. So, we have that function very well defined, which is monotonically decreasing function of charge density. Now, if you look at the other part, which is what we call Lennard-Jones type, that term is looking at the monotonically decreasing function of R with a cutoff between nearest and second nearest neighbor. So, now we can also create Z I and Z j, which are the function that we are looking at, almost similar to what we use in Coulomb potential. So, we are looking at jth term in the sum, which has contribution to density at site I due to atom j, and R I j is the distance between I and j. So, to complete the specification of EAM, one often has the repulsive contribution to of the form which is phi I j r z I r and z j with r is the distance between them. So, if I combine these two ideas, you have the embedding function and which has electronic density functional, and then the third one is pair potential, which is defining the repulsion. So, the first term is defining what we call as cohesion, and the second term is defining repulsion. So, these are the two attractive and repulsive forces that you saw in Lennard-Jones. Now, in this case they are dependent not on just the potential energy and the lattice distance between them, but they are dependent on the density functional approximation and use of density functional term rho I, which defines the cohesive force for an atom to be embedded into this cloud of atoms. And then there is a repulsion force as the atoms come together. So, you have the cohesion term and the repulsion term together, that makes this metallic potential. So, it has an inner hard core and then there is a valence electrons around it. Valence electrons are delocalized, so that they are all over the place. Pair potential do not work very well because they are delocalized. Strength of the bond decreases as density increases because of the Pauli's principle. So, now we are following that with density functional approximation. So, if you look at a surface, Lj potential predicts the expansion, but metal as you know contracts. So, what we are doing is that embedded atom method or glue model is better with Daw and Baskis. So, what we are looking here is that this kind of formulation, which includes both the cohesion as well as the repulsion term, we are able to calculate face centered cubic metals very well. And so, copper, aluminum, and if you look at antimony and all the other elements that you are going to look at, that you can really calculate well. However, you for BCC crystals that does not work as well. So, this is EM potential and it has 6 adjustable parameter for understanding of multiple influences in the construction of this atomic potential function, and these are the 6 parameters that are fitted in order to really come up with the understanding about metals and alloys like copper and aluminum. So, if you look at here, these parameters are equilibrium lattice parameter, which is sigma. We look at sublimation energy, vacancy formation energy, and the 3 elastic constant for cubic crystal. So, in contrast, we recall that Lennard-Jones potential has 2 parameters, which is only sigma and the eta, which is the potential energy function here, but in our case now we have 6 parameters. If you look at EM potential, there is a lot of literature available there, and there have been extended EM potential, the later version of EM potential, all of that by Daw, Baskis and Foils, and they essentially provide us good understanding of how we can improve the understanding of metals using molecular dynamics simulation. We can even use Monte Carlo to a certain extent in some of the cases if there is radiation transport involved in that. So, now we understand that for metals we cannot use Lennard-Jones potential because they do not predict the behavior correctly in terms of their elastic behavior as well as the behavior due to relaxation. So, if you look at the parameters that we have included here, which is the equilibrium lattice parameter, the sublimation energy, vacancy formation energy, and elastic constant, these are the properties, or these are the empirical data that is modifying this potential function in a way that it correctly predicts the behavior of metals. So, let us stop here and we are going to move forward with the potential functions which are now bonded type, and then we will look at some understanding about with a simple water molecule. We will understand how the bonded potential have the 2 terms, which is intra and inter, and how they work together in order to predict the entire behavior of the number of water molecules. Thank you.